This week sees extreme heat across England, particularly in the south, where temperatures may well exceed 40 degrees Celsius. The last time this happened was in 2022, and for the railway, and indeed the built environment at large, we saw severe impacts as a result of this. There is a fantastic document that's worth downloading to understand what the impacts are on the railway, because the Climate Change Act requires Network Rail and other public and private bodies to understand climate change, not just in terms of emissions reduction, but the response to climate change, what's called climate resilience, actually having infrastructure that can survive those changing conditions, of which temperature is a key one. It's a fantastic document. You can just download it by going to the just googling Network Rail Climate Adaptation Report. The fourth edition is a PDF out there available, well worth downloading. Within it are several graphics, really useful graphs that explain, that allow us to understand the impacts from different forms of climate. In the case of heat, well, this graph is very useful. It shows Schedule 8, which is the kind of the daft wooden dollars way that the infrastructure part of the railway gives money to the train operating part of the railway if there's some infrastructure problem that delays trains. So Schedule 8, in a way, is a measurement of delay minutes. It's about its only useful application is in collecting those statistics. What this graph shows is overall climate impacts since 2006 up to 2024, and you can see that that number overall is absolutely increasing from about £50 million a year up to £150 million. Particularly for this discussion, what's really interesting here is you can see heat, the actual impacts from heat increasing over time there, shown, the breakdown of different climate impacts, shown there, heat in red, and you can see that that is also increasing quite dramatically over time with that big lump in 2022. Another graphic that's quite useful is breaking down those impacts, those climate impacts, by discipline, by technical discipline. So you can see that the orange there is heat. The biggest by far, you see that big orange blob, is for health and safety and welfare, so staff safety. We'll get to that in a minute. But at the top there, you can see track is also very heavily impacted by heat. Indeed, the Climate Change Adaptation Report goes through lots of different ways in which heat specifically impacts on the railway, alongside lots of other things. Water is another key threat from climate change to the railway. So track buckles constantly get talked about. If you're hearing a news report about the heat, then yes, people are going to be talking about track buckles. How do we manage track buckles? How do we manage those thermal forces? Well, of course, the issue here is that steel, the rails are made of steel, and steel expands in the heat. And so that expansion has to go somewhere. Now, there are different ways that we used to manage this. We still indeed have fish-plated joints, joints that are essentially two separate 60-foot lengths, 18 to 8 meter length rails connected by joints that have a fish plate either side, bolts through them, and an expansion gap that closes or opens depending on how hot it is. In winter, those joints are open, and in summer, they might well be closed up. The problem with those joints is that under traffic, they have a nasty habit of disintegrating and derailing trains, which is why we moved very much away from them in the middle of the last century. And they're also extremely challenging to maintain. There are hundreds of joints in any given stretch of a mile of mainline. You may have 100 joints to maintain. That's a serious labour burden at a time when we have fewer and fewer people actually out maintaining our tracks. So the other way that we can manage, connect up rails to manage those forces is through welded joints. Now, when we weld two bits of rail together, we don't just do it at any given temperature. No, we actually make sure we cut a specific gap in the rail, or we leave a specific gap in the rail, and we actually pull those rails together before welding them to make sure there is a certain tensile strength in the rail. Because if you have a length of rails are essentially long and thin. In tension, so if I'm pulling them apart, they maintain their shape very nicely. As soon as there is a compressive force, they buckle, right? That's the issue with buckling track. What we do with the rails, with welded rails, is that we actually apply a tensile force to keep those rails to shape so that they can cope with higher and higher temperatures. Now, in the UK, we have a temperature at which you move from tensile to compressive stress. It's called the stress-free temperature of 27 degrees. For legacy installations, actually new installations are using higher temperatures now, and we're probably going to move into a situation where we might well consider case-by-case basis of what that stress-free temperature needs to be. More on that perhaps in another rail natter. In the meantime, we pull those rails together, weld them up, and so those forces, those longitudinal forces, are distributed through the track. So we have stronger track materials, heavier track materials, concrete sleepers, and also crucially the stone that supports the track, the ballast. We have what are called shoulders here, either side of the track, that actually help to maintain its lateral stability to avoid buckles happening in the first place. Of course, if you can limit the amount of the temperature, the sun getting into those rails, you can also keep those rail temperatures down. A kind of a rule of thumb is that if you have a given air temperature, then the rail temperature might well reach 20 degrees hotter than that. So for 40-degree air temperature, you might have 60-degree rails. Painting the rails white is one way to manage that, particularly in weak areas where you've got switches and crossings, junction areas, you might well paint the rails white, over bridges perhaps as well. Italy does this pretty much for their whole network. We are a bit more selective. In more extreme ways, you can use different track forms. So slab track, for example, being used for the majority of HS2, used for lots of bits of kind of suburban rail around the world, is much more resilient to high temperatures. It's much better at keeping the rails in place in those higher temperatures. But it's much more expensive, of course, to install, even if it is then essentially maintenance-free from that point, and perhaps not suitable for all conditions. The issue, of course, is, well, not of course, the issue is that plain line tracks, so just two rails going off in both directions, is less of an issue, to be honest, from buckling, as those busy, complicated areas like this, like Clapham Junction, like Victoria down in London, those areas of complex S&C, or busy S&C, switches and crossings everywhere, that are what we call unstressed S&C. It cannot cope with those compressive forces. It's too weak. It will fall to bits, buckle, disintegrate under traffic. This is bad, requires speed restrictions or closures. What's the way to fix this? Well, track renewals. Replacing those track materials with new, modern S&C that can be stressed allows you, so this is Thameslink renewals near London Bridge about a decade ago now. This whole area can now run at 59 degrees Celsius. So you can run trains through here at full speed, basically with a 39-degree air temperature. So it gives you an idea of the fact that we can run a railway if we renew the track. So track renewals are climate resilience, are climate action. What about other parts of the railway? Overhead electrification. It is absolutely, a railway is incomplete without overhead electrification, frankly, but it is also vulnerable to heating. Again, we have overhead cables, overhead wires, overhead lines. As they get hotter, as they're metal, they will expand. And how does that expansion get? Well, it results in sagging. You have sagging. Now, we deal with that by having tensioning systems that actually tension for the sag. So as the cables expand, there's overhead lines expand, then the tensioning systems account for that. Up to a point. And indeed, fairly new systems installed in the UK, overhead electrification systems, were designed to cope with 38-degree air temperatures. You'll be glad to know that standard's been updated. But of course, we have lots of legacy electrification that is either doesn't have auto tensioning at all or isn't designed to cope with the temperatures that we get nowadays. So that can also be a challenge requiring speed restrictions, because if you have a sagging cable, that can get snarled up in the pantograph and result in dewirement and a closed railway. What about people on trains, though? Because the staff and passengers on trains, not all trains have air conditioning that can cope with high temperatures, even 35 degrees, let alone 40 degrees. So that is a major challenge. But what about our signalling systems? Because as we have centralized the operation of our railway into larger and larger rail operating centres, nerve centres of large regions of the railway, you can see the kind of the workstations there. If you've got a whole team in one of these fantastically modern workstation, kind of working environments, and the HVAC fails or the aircon is not up to snuff, they can't work in those conditions. They go home, the railway shuts. That's the end of that. Potentially worse, if you have the room with all the solid state interlocking in it, all the basically solid state hard drives with all the signaling system in it, and they all melt because the air conditioning has failed, your railway is out of action for days, weeks, months, maybe. So centralization is in many ways good, but it creates these new challenges. So for trains and for our rail operating centres and those centralised nerve centres of the railway, air conditioning becomes a absolutely safety critical part of that design and needs to be taken very good care of. Of course, in these extreme temperatures, as we saw in 2022, bits of the railway can just melt or burst into flames. And there is, less and less you can do about that in extreme heat. And extreme heat is what we're going to be seeing more and more and more of. There's more for us to do. And of course, the big challenge is, do you divert funds away from expansion and capacity increases of the railway, so therefore reducing carbon emissions by driving modal shift, just for the sake of climate resilience? Or do we need to invest more in our public transport systems to get people off the roads, which themselves have got their own issues of buckling, melting, and so on?